In this section, I'm going to be talking about dimensionality reduction. In most real-world problems, there are training instances that are not spread out uniformly across all kinds of dimensions. Some features can be constant, while others are highly correlated. And as a data scientist, you may have too many features on your hand to analyze effectively. Sometimes data has hundreds of thousands of columns. Again, as an analyst, you should be able to identify the features that can be omitted before applying data mining techniques. The nice thing about dimensionality reduction is that it removes the features without losing too much information. And there are some common techniques with factor analysis, principal component analysis, and linear discriminant analysis. Now let's start with factor analysis. I do like a website I'm going to go to. It's is from sciencedirect.com. So I'm going to go ahead over here and just type the URL for you. So sciencedirect.com, topic psychology factor analysis. Now, on the website, it mentions that factor analysis is one of the oldest structural models. It's been developed by Spearman in 1904, so it's been around for a while. And I really like his definition because he says that Spearman tried to explain the relations or correlations among a group of test scores and suggested that these scores could be generalized by a model with a single common factor, which he called intelligence, plus a unique factor for each test. And that really sums it up pretty nicely. The purpose of factor analysis is to account for the intercorrelations among an amount of variables. It is a statistical method and explains the underlying variance and covariance structure of observable data. What is the common goal here? It's to be able to considerably postulate a set of common factors. Considerably, they should be fewer than the number of variables that are available. Now, these factors are random variables that cannot be observed. So I'm going to switch gears over here and go to wikipedia.com factor analysis. And as you can see, there is a nice model that can explain how this will work. So suppose you have a data set containing n observable variables. Then you're able to apply a factor analysis model to determine the relationship between the variables, the variance, the covariance, which can be partitioned into common variance, unique variance, and commonality. Now, this is a very nice equation. It's pretty lengthy, but for the most part, it should explain what's going on, where you have over here x1 to xm. Those are your observable variables. You have mu sub m, which is the means, respectively, and then you have factors f1, f2, f sub of n. So just really quick, factors, they're sometimes called latent variables, but at the end of the day, what you're really trying to do with factor analysis is you're trying to group variables into homogeneous sets, and you're trying to allow researchers to investigate hidden, un, unmeasurable variables from the measurable variables. Now let's try to explain all this via an example. So I am going to be using a data set from ESPN, and as you can see here, you can find the URL, espn.com, ESPN, page 2, sports. Now, ESPN, they have identified 10 categories or skills that go into athleticism, and they asked 8 panelists to assign a number from 1 to 10 to the demands each sport makes of each of these 10 skill sets. As you can see here, there's a key at the bottom, and the skill sets were endurance, strength, power, speed, agility, flexibility, nerve, durability, hand-eye coordination, and analytical aptitude. So what they ended up doing is they, as you can see here, totaled and averaged the responses to arrive at a degree of difficulty number for each sport on a 1 to 100 scale. Now, that number places the difficulty of performing each sport in context with the other sports that were rated, which is a very fun data set to work with. And as you can see here, when totaled, boxing, ice hockey, football, basketball were ranked as number 1, 2, 3, and 4 when it comes to the degree of difficulty for that sport. So I went ahead and downloaded this data, and I am going to use for my example when it comes to dimensionality reduction. So I just copied and pasted here, and as you can see, this is my key. Again, endurance, strength, power, speed, agility, flexibility, nerve, durability, hand-eye coordination, and analytic aptitude. Now, these are going to be my components that are going to be taking a look at. And what I'm going to try to do is apply factor analysis to postulate a set of common factors that are going to be fewer in number than the 10 components that are identified, as you can see on the screen. So first things first, I'm going to import pandas as PD. I'm going to be reading my CSV file. I called it toughest sport by skill.csv and load into data frame and then look at the first 5 records. And voila, as you can see, boxing, ice hockey, football, basketball, wrestling popped up as the first 5 records, which also show that they were the sports that demand the most from the athletes who compete in. And this was based off of the word of panel of experts. And these panel of experts were made up of sports scientists from the US Olympic Committee, academics who study the science of muscles and movement, and a few journalists. All right. So data frame is always fun to watch, but I always say it's much better to try to plot it in a box plot to be able to delve into the data further. So I went ahead and plotted the data. And as you can see, I was able to look at the the min, the max, the Q1 median, Q3 for endurance, strength, power, speed, agility, flexibility, nerve, durability, hand-eye coordination, and analytical aptitude. And as you can see for flexibility, a number 10 was assigned to gymnastics and 1 for fishing. When it comes to power, again, a value of 1.25 was applied for fishing, shooting, equestrian, billiards, and on the flip side of that scale, weightlifting required the most amount of power. Endurance, you have track and field distance rated at number 10, or was assigned a value of 10, which ranked number 40. Swimming was ranked overall 36, but second or third actually in endurance. So this actually helps explain the data set a lot further. And again, my goal is to find a sophisticated way to perform modeling and create training validation data sets without overfitting. And as you can see here, deciphering the various data patterns could be very complex because there's a vast amount of data. Even as you can see here, with box plots, there's still a lot of data to decipher. And this is always a challenge for data scientists. And the question is, what are the right variables that I need to use for analysis? And the key here with factor analysis is that I'm trying to boil down a couple of factors that are the most informative when it comes to the dimension. So let's start jumping into the data further. So the first thing I'm going to go ahead and do is drop some of the columns. I'm going to go ahead and drop rank, total, and sport to just look at the skills further. So I'm going to write DFOG drop. I'm going to drop sport, total, and rank and create a new data frame called DF. And the next step, I'm going to try to type df.describe. Now I know you haven't used the describe method for a while, but the describe method will provide you descriptive stats that will include the 25th, 50th, 75th percentile, the count, mean, standard deviation, minimum, and the maximum, which you saw quite clearly in a box plot, or in this case, multiple box plots. Now, just for fun, I'm going to check if there were any values that were null. And as you can see, none of them were null. And you can also type. You can always check for duplicates by typing df and then open square bracket, df.duplicated, close square bracket, and then print. And as you can see here, we don't have any duplicate values. Now, in the next part of this lecture, I'm going to talk about scree plot. Now, what is a scree plot? Again, choosing the number of components or factors to extract is the goal of factor analysis, and we're trying to reduce our set of variables down. So we would like to have some sort of criterion for selecting the optimal number of components that are, of course, smaller than the number of items. In this case, in our example, we have 10 items or 10 skills. We would like to reduce it to a value that's much lower than that. And that is where scree plots come into play. We're going to use a criterion to choose the number of components that have eigenvalues that are greater than 1. So there is a good paper just for reference. This is from Brian Habing, University of South Carolina, October 15, 2003. And it talks about exploratory factor analysis. And what I'm going to go ahead and do is I'm going to jump a few pages to page number 4, Kaiser criterion, eigenvalue more than 1. And it says over here, when it comes to the scree plot, take the number of factors corresponding to the last eigenvalue before they start to level off. And when it comes to the Kaiser criterion, eigenvalue more than 1, take as many factors as there are eigenvalues greater than 1 for the correlation matrix. Now, hopefully this will make a lot more sense when we plot a scree plot. So I'm going to go ahead and copy and paste some code. And really quick, importing pandas, matplotlib, seaborn, and then from factor analyzer, I'm importing factor analyzer. I'm printing the number of columns, so in this case, the number of skills. I'm building the factor model, finding the eigenvalues, graphing the scree plot. All right, so let's have a look. Voila. Here is our beautiful scree plot, y-axis eigenvalues, x-axis factors, and as you can see here, the horizontal line in red, that's where Kaiser's criterion eigenvalue equals 1. So again, we want to take as many factors as their eigenvalues greater than 1. So in this case, you can see that there's about 4 or so. But one thing about scree plots that you have to be careful with is that take the number of factors corresponding to the last eigenvalue before they start leveling off. So you can see it starts leveling off here. Eigenvalue of 1 is 4, so we want to take 3 factors. So really quick here, I'm going to leave you a link from Wikipedia. If you click on, you can see here scree plot. Scree plot again is used to determine the number of factors to retain an exploratory factor analysis. And as you can see here, this is the plot that is shown on Wikipedia. And this is what we have over here that we were able to generate. And at a value of 3 to 4, that is your elbow, where the eigenvalues seem to be leveling off. So according to Raymond Cattell from the scree test, the elbow of the graph is at 3. That's where the eigenvalues seem to be leveling off. Therefore, the number of components or factors are to the left of this point. In this case, 2 factors should be retained as significant. Now we have another test under our disposal. It's called the Kaiser-Meyer-Olkin KMO test. Now the KMO test, it measures the proportion of variance that might be common variance among the variables. So I'm going to go ahead and click on a link from IBM. And you can see that the Kaiser-Meyer-Olkin measure of sampling adequacy is a statistic that indicates the proportion of variance in your variables that might be caused by underlying factors. High values, close to 1, generally indicate that a factor analysis may be useful with your data. If the value is less than 0.5, the results of the factor analysis probably won't be useful. All right, so what I'm going to go ahead and do is copy and paste some code, import calculate KMO, click run. And as you can see from the KMO scores, they're between 0 and 1. And again, to repeat, this test indicates the suitability of my data for structure detection, and it's indicating the proportion of variance in my variables that might be caused by underlying factors. So in this case, endurance, strength, power, speed, agility, durability, analytical aptitude suggest that these variables are appropriate for factor analysis. Now in the last part, I want to again determine my factor loadings and my communality for each variable. So I'm going to go ahead and copy and paste some code. And again, factors equals 2, we were able to determine that from our scree plot. I'm going to go ahead and build my factor model, obtain my factor loadings. Gonna do some cleanup here, and I am going to obtain my communality. Now again, communality is a proportion of each variable's variance that can be explained by these factors. So I'm gonna go ahead and run. Beautiful. And as you can see here, for my factor loadings, I was able to determine my factor 1 and factor 2 and my communality for each of the skills that were identified. Now this is a little tough for me to read, so I'm gonna apply a quick little trick here to merge those two together and be able to examine my loading pattern and my communality. And you can see right off the bat here, you can see the factor that has the most influence on each variable. Now, loadings that are close to -1 or 1 indicate that there is a strong influence of a factor to that variable. So, loadings that are close to 0 indicate that usually the factor has a weak influence on the variable. So, right off the bat, you can see factor 1 indicates that the factor strongly influences the following variables. In this case, strength, durability, power, speed, and factor number 2 seems to influence highly hand-eye coordination and analytical aptitude. Now, when it comes to communalities, the closer the communality is to a value of 1, the better the variable is explained by the factors. So in this case, these two factors explain the factor well, where when it comes to the nerve, communality is close to 0, therefore those factors do not seem to explain well the skill nerve or that variable nerve. Just as a word of caution, sometimes the value for communality could be greater than 1. That is usually an indication that there are too many or too few factors that are chosen and insufficient data points. So it seems like we have a good sweet spot here. Now, just for fun, I'm going to go ahead and copy and paste some code. In this case, I'm going to build a factor model with 3 factors. I'm going to go ahead and run it. And I'm gonna apply my fun trick here to merge all those different data frames together, and voila. You can see here my communality value is greater than 1, not by much. So that's what we're talking about. So if we go back to the scree plot here that we built, if you remember, this was our elbow. It occurred at a factor, a value of 3. Therefore, the recommendation was to select 2 factors. And as you can see from our analysis, that is the case. Is that a factor of 2 would have been best suited for our data set that we are working with. So how can we interpret this table better? Well, factor 1 influences strength, agility, durability, power, speed. Those are all skills that are attributable to physical performance. Factor 2 seems to influence hand-eye coordination and analytical aptitude, which is a technical element. That's the best way I can explain it when it comes to that domain, the cognitive psychomotor domain. It's a technical element, which typically encompasses technical movement, the stance, the footwork, the strikes, the clinch, and how they should be executed according to key performance points. Now, the interesting thing is when we actually had three factors, you can see factor 3 seemed to influence durability and nerve, which are psychological elements. Typically, athletes' will, motivation to reach goals or objectives. And being able to access this is critical, of course, when it comes to not only competition, but training. Now, just for fun, I'm going to rename factor 1 to physical, factor number 2 to technical. I'm going to melt this data frame so I can plot it in a bar plot. So I'm going to go ahead and copy and paste some code. And I'm going to go ahead and run it. I'm going to look at the first 5 records. Super. This is what it's going to look like. And the last part, I'm going to plot it. So I'm going to make a bar plot. Going to use the x-axis for factors, y-axis for the value. My hue is going to be my metrics. I'm going to go ahead and run it. Awesome. So this is exactly what we have been talking about. When it comes to the loading pattern, you can see right off the bat that the factor loadings associated with hand-eye coordination and analytical aptitude are less influential in the physical factor than the technical factor, which makes absolute sense. Therefore, the physical factor strongly influences the following variables, and to a big extent, the strength, durability, power, speed, agility, endurance, flexibility. As you can see here, those values decrease when it comes to the physical factor. But when it comes to the technical factor, the hand-eye coordination and the analytical aptitude, were explained pretty nicely with the technical factor. So to sum up, in these results, 2 factors were extracted from the 10 variables. That is outstanding. And to add on to the interpretation, when it comes to the communality, a value of 81% of the variability in strength is explained by the 2 factors. Very cool. So again, it was very interesting examining these factor loadings because we were able to understand what constructs underlie the data. Not only were we able to also account for the intercorrelations among the 10 skills and variables, but we were also able to postulate a set of common factors, in this case 2, which are considerably fewer in number than 10. Now, these factors are random and not that easy to observe, count, or measure directly. But as you can see, they can be presumed to exist and can explain that underlying variance, as you can see by the communality and covariance structure of that observable data, which resulted, as you can see here, by 2 factors, which is potentially fewer unobservable variables, which are your common factors. This is fantastic. Again, this is a great tool to understand and to use among the techniques for dimensionality reduction. Now, this concludes our section on dimensionality reduction.